What if I told you that every single living thing, from a tiny bacterium all the way up to you and me, runs on a set of chemical rules that are completely non-negotiable? Yeah, these aren't just suggestions, they're the constants that act like a chemical compass for life, guiding every single biological process with just incredible precision. So today, we're going to pull back the curtain and uncover them.
Okay, just for a second. Imagine the most critical machinery in your body just suddenly shutting down. That is exactly what we're looking at right here. The entire function of a protein depends completely on its exact shape and its charge. I mean, look at the difference here. One works, one doesn't. And all it takes is a tiny, tiny shift in the chemical environment to flip that switch. That's the biological imperative we really need to get our heads around.
All right, so to understand that super delicate balance, we've got to start with the molecule itself. Think of it like a character in a story, right? We need to figure out its innate personality, its fundamental chemical fingerprint, before we can even begin to predict how it's going to act on the stage of life.
So, our first tool for figuring this out is something called the Acid Dissociation Constant, or Ka for short. The easiest way to think about it is as a measure of a molecule's generosity with its protons. As you can see here, a bigger Ka value means it's a stronger acid. It's way more willing to just give away that hydrogen ion. Now, a really quick but super important clarification here. You might also hear about another value called Ka. Please don't get these two confused. As we see here, Ka is all about an acid giving up a proton. Kd, on the other hand, is about a protein letting go of something it's holding on to. Two totally different jobs. For our story, we are sticking with Ka. So what's the problem with using Ka directly? Well, honestly, the numbers are a total mess. They're often these tiny, clunky values in scientific notation, like 1.74 times 10 to the minus 5. I mean, come on, trying to compare those in your head is just not going to happen. There has to be a better way, right? And thankfully there is. The solution is called pKa. This is where the sheer elegance of logarithms comes into play. By taking the negative log of Ka, we can transform those messy, complicated decimals into a clean, simple scale of numbers that we can actually use. It's just a beautifully simple fix. So how do we read this new, cleaner scale? Well, it's an inverse relationship. The stronger the acid, the lower its pKa. But here's the real magic. The pKa value isn't just some random number. It is the exact pH where that molecule is perfectly balanced, 50% holding onto its proton and 50% having let it go. This right here, this is the molecule's unique chemical fingerprint.
Okay, so we've got our molecule's fingerprint. It's pKa. But a character doesn't just exist in a vacuum. Now we need to understand the world it actually lives in, the environment that's going to shape its every move.
And that world is defined by pH. The pH scale is really just telling us how many hydrogen ions are floating around in a solution. But you have to remember, just like pKa, it's a logarithmic scale. A change of just one pH unit, say from 7 down to 6, means that environment is now 10 times more acidic. These small numbers represent absolutely massive changes. And this, my friends, is where it all comes together. We have the molecule's internal personality. It's pKa. We have the character of the external world it lives in. It's pH. So now it's time for the main event. What happens when these two finally meet? So the crucial question really is this. How does a molecule's fixed, unchanging pKa actually relate to the constantly changing pH of the world around it? I mean, how do these two numbers even talk to each other?
The answer is this absolutely beautiful relationship, the Henderson-Hasselbalch equation. This thing is the master key, the biochemist's secret superpower. It directly connects the pH of the environment to the pKa of the molecule, and that lets us predict the exact ratio of the two forms of that molecule. It is the bridge between the outside world and a molecule's internal state.
But hey, you don't need to be a math whiz to use it. This whole equation really just boils down to three simple, powerful rules. If the pH of the environment is lower than the molecule's pKa, the molecule hangs on to its proton. If the pH is higher, it lets it go. And if they're exactly equal, you get that perfect 50-50 split. Seriously, it's that simple.
Okay, so we have an equation, we have some rules, cool. But what's the real-world payoff? How does this chemistry actually translate into the, breathing, functioning, stability of life itself? And here it is, the killer application, buffering. That special point where pH equals pKa is the absolute heart of a buffer zone. By having tons of molecules in this 50-50 state, biological systems can soak up extra acid or base without the pH going haywire. This is exactly how your blood maintains an incredibly stable pH, protecting all those delicate protein machines we talked about.
So let's just trace our entire journey one more time. We started with a fundamental constant, Ka. We made it way more intuitive by converting it to pKa. Then, we used the Henderson-Hasselbalch equation as our master key to connect that molecule's pKa with the pH of its environment, which ultimately lets us predict the outcome, its ionization state, and its biological function.
And what's just so incredible is that this isn't some academic exercise. These constants, these equations, they are literally the operating system of life. They're the fundamental rules that life meticulously uses every single second of every single day to manage its internal chemistry and maintain that perfect functional balance.
You know, when we really understand this language, from a single proton's tendency to leave all the way up to the buffering power of an entire system, we can't help but gain this deeper appreciation for the insane level of chemical precision that is required just to be alive.
And that kind of leaves us with one last thought to chew on. If life truly depends on maintaining this incredibly delicate, precise chemical balance, what happens when external factors, whether they're in our environment or inside our own bodies, start to disrupt it?